Since I didn't know about who exactly will come, I prepared lectures which does not assume any knowledge about algebraic groups, but so actually I want to assume that with algebraic groups, Lie groups, some algebraic geometry, Lie groups and differential geometry, and measure theory. I know that I cannot assume it to full extent, but I mean, so I will try to fill some gaps, and I will need feedback from you about it. But officially, I'm doing so. Now, what I want to do in this course is to discuss algebraic groups from algebraic, geometric, and analytic point of view, and I want just to start with example. I want to study things like GLM K field, but also might be a ring. So in particular, I want to study guys like GLM-Q, GLM-Z. Now, Q is a countable field, but actually, as I think I do want to assume that you know, Q embeds into which is locally compact. So this is an introduction. So this is a countable field, and it embeds into some bigger ring, which has a locally compact structure, and this is basically a product of the rings and the periodic fields, which again I want to assume that you know about, and these all are local fields. So when we study such a guy like GLM-Q, every time we embed it into the product, well, so this is a linear group over a ring, and I can understand this group because basically it is a product of linear groups over fields, which I can study, and all these guys here are just algebraic groups over fields, but not just algebraic groups over fields. They're algebraic groups over local fields, so fields with topology on them, and so I can use tools from the theory of algebraic groups in order to study those, but also I can use tools from the theory of Lie groups, which I have to develop over those fields, and from measure theory, ergodic theory, etc. So I can actually do some analysis. So today what I want to do is to leave all this behind us and to start with a fresh topic. So again, I will not do algebraic groups today. I will ask about. I will try to figure what is the common knowledge of us about it. So I want to start something fresh without any assumption taken for. Yeah.
So when you say you want to study this, what do you mean by that?
So I mean by this that I'm not describing exactly what I will do this course. But you're asking now to do. But I will ask questions and try to answer them and develop some theories which are motivated by the structure of those groups. I want to say something intelligent about it. So
structure questions or stuff like that?
Yes, mostly I will be interested not in questions, not in problems, but in describing tools that were developed and theories that were constructed in order, motivated by asking questions about these objects. So in this course I will certainly try to develop the theories to be developed. Symmetric spaces and buildings. And what else? Well, maybe this is just an example. There will be a list here. So maybe analytic geometry is the topic of today. And this topic, this is the title of today's talk, requires nothing, basically. Of all these enormous background that I'm assuming. This is what I'm doing today. And chapter 1 of these topics, so probably I should pause and ask more questions about this introduction, but I didn't give enough details, but I will not. Again, everything here was just for me. And today we start with analytic geometry. And I start with fields with absolute value. Such as the p-adics, which I assume again that here and there you've already seen. But I will, and I'm assuming that you've seen the theory that this chapter 1, fields with absolute value. You've seen this, but I'm just reminding you. What is it that I'm assuming? So here's the thing. But actually, I mean, if you haven't seen what I'm saying now and you want me to expand, please ask and I will explain later. Okay? Is a field with an absolute value if, well, K is a field. This guy is a map from K to 0 infinity, such that the absolute value of 0 is 0. On K star, the multiplicative group of non-zero elements getting a map to I'm not getting 0. So 0 is the unique guy with absolute value 0. And this is a multiplicative homomorphism. Famous triangle inequality. So example, the first example would be the trivial absolute value on a field. Just take any field and define the absolute value of x to be, well, 0 or 1 if x is not 0. This is trivial, this is not interesting. I will always assume, unless saying otherwise, that my absolute values are not trivial. By the way, if they are not trivial, I will not write it down. Then I have guys which gets values which are not 0 or 1. So powers of those guys we get arbitrary high or arbitrary low absolute values. So my absolute values, if not trivial, are always unbounded. Next examples, I guess, are familiar. Now, these are the standards, absolute values on the rings or the complex. Here's a remark. If k is an absolute value, field absolute value, and if alpha is whatever number, real number between 0 and 1, then you should check that this is another. Field is absolute value, so it satisfies all these things.
Three also?
Yes, this is by convexity of those functions. It's just convexity.
I think you can do that.
Yes, it's not arbitrary alpha. Bounded by 1, I guess. So, already these give one parameter classic examples. Okay, so here is another example. Take the periodic absolute value on P, which is given by that. A prime P. And every rational number I can present uniquely as number of this form, right? I can take R here is some integer. I can take the a power of P out and then get now a fraction which is prime 2P, and I'll define its periodic absolute value by, well, here I can take any base alpha. Alpha is
Alpha smaller than 1.
alpha smaller than 1. Sorry, alpha should be smaller than 1. Usually, we take alpha to be P inverse here. This is the usual formula, but whatever alpha will make sense. So you should check that this is an absolute value. This is very easy. I'll give another example. I can take for a field F, I can take K to be the field of rational functions over F, and I can take the absolute value, which is assigned to a ratio of polynomials, the value alpha, big F, degree of F minus degree of G, and again, alpha should be in this range. This is another example of an absolute value. Or maybe observation. K becomes a metric space, a particular topological space, by, well, the obvious distance given by that absolute value. Now, the completion of K with respect to that metric, the metric completion is a field again. And the absolute value naturally extends as the metric usually extends to the completion of the metric space. Moreover, so are those things, are other people here that didn't see any of those stuff in the past?
No question.
Good. So if I'm wasting your time, just stop me. Else, the absolute value extends uniquely to an absolute value on any finite extension, finite field extension. Or actually, it follows any algebraic extension as well. And so in particular, it extends to an algebraic closure. So I'll give it now. So the completion of this guy is the field of Laurent power series over F. And the completion of Q with respect to any of those periodic norms. They are all metrically equivalent. And the completion of Q will be QP. So we have, again, the periodic absolute value on the periodic field. And moreover, the periodic absolute value on the periodic field extends to any algebraic extension ends also to the algebraic closure. Now here's a fact that we have seen in the course I gave last year, that the algebraic closure of the periodics with this extended absolute value is not complete anymore, but one can complete it. So here's a fact that I feel. Yet another fact, just a minute.
I'm not sure about the uniqueness and you mean complete field or because if you have a number field, each
Oh,
point
yeah. Extends uniquely if k complete. Thanks. This is not correct. It extends uniquely if k is not complete. Of course. Now the periodic field is complete, and so we can extend it to the algebraic closure. And where is the remark that I want to make? K algebraically closed, then the completion of it is algebraically closed as well. So I just want to put on the board this symbol, CP. So this is the metric completion of the algebraic closure of the periodic field. So this, in the theory of periodic numbers, this behaves, the analog over the rings will be just the complex numbers. This will be the metric completion of the algebraic closure of the field of real numbers. Only the algebraic closure is just an extension of order 2, and the metric quantity is already complete. So here the story is a bit more complicated, but this is like an analog. Okay, but most of the time, my fields will be here of the periodics. This guy is called Non-archimedean. If it satisfies, instead of this, the axioms P prime, the absolute value of x plus y is smaller than the maximal among the absolute values of x and of y. And this called Archimedean. Is not as usual with the unfortunate definitions by double negations. Okay, we know those axioms. Now observation. If we have a non-Archimedean guy, then the set O, consisting of all guys x in K, such that the absolute value is smaller than 1, is closed by, well, axiom 2 that I just erased to multiplication, and by axiom 3 to addition. So this is a unitary subring. So the subring containing 1. The absolute value of 1 is 1. Why? Yeah, because the absolute value is a homomorphism. And one is the unit of the multiplicative root of the field, right? Which is exactly what you said. Now, here's another. M is a smaller die. This is called the x's, such that x is actually less than 1. Is I claim that M is an ideal. This is clear. But moreover, everything which is not in M is actually a unit, right? Because everything in O, which is not in M, has an inverse, because it's in every non-zero element in K as an inverse, and the inverse should be in O as well, because of the multiplicativity of the absolute value. So if the absolute value is 1, also the absolute value of the inverse is 1. So everything which is in O but not in M is invertible. In O. So that makes M a unique maximal ideal. M is a unique maximal ideal. So the quotient ring, noted F, is a field. Is called the residue field. Okay. Or of K, absolute value. Right. Okay. So basically this sounds like a very rich theory, and we just know some examples which I'm raising now. But actually, what I want to say is that what I want to say next is basically we know all examples. Or we know many examples. Or I should say, there is no much more than the examples we know. And this is the concept of Ostrowski theorem. Let's start by Ostrowski theorem, which describes all the absolute values on Q. Always the trivial one. We've seen the periodics. And when I say the periodic, I mean the periodics with the general alpha, as you remember, not just the standard P inverse to the evaluation. And of course we have the real, or the standard absolute value. And it's not the only one up to power. I can take it to the power of alpha. And so the theorem is that this set is exclusive. And again, I want to assume that you've seen this theorem. I will prove it, but not in full details now. Okay? So let's start assume that this guy is non-Archimedean and show that it is one of these two. Now, we have this guy O here, and this is unital, so it contains 1. So it contains, it is a ring, it contains 1 plus 1, it's 1 plus 1 plus 1 plus 1, and minus 1, etc. So, we have Z is in O, no doubt. M in O is maximal and prime. So we get that it's pullback under this map. You remember that the pullback of a prime ideal is prime. Is prime. I mean, it is not everything, this for sure, because 1 is not. Sure that. The absolute value of 1 is 1. We said that. So what could it be? What are the prime ideals in Z? So Z is an integral domain, so the 0 is a prime ideal. If this is the case, then what can we say? Oh, sorry. No. This means that all the integers have absolute value. What? All the integers are in O but not in M. They satisfy this equality sign here. So all the elements of Z have absolute value 1, but every element of Q can be expressed as the ratio of 2 elements in Z, and the absolute value is multiplicative, and this means that all the elements of Q have absolute value 1. This means that this guy is critical. Other option is that this is a proper ideal, and this means that this is P for some prime P. So in that case, if we denote the absolute value of this P, of the generator of the ideal, by alpha, and this is an element of M. So this is something which is in O, so it's less or equal than 1. Oh, slightly less than 1, because it is in M. So, so we get, now I guess, maybe you don't notice, but this N that I'm writing there is squarish. The font. So this is an ideal, not a number. We get that if we have an element of that form, in which if M is prime 2P, then it is not in that ideal. So the absolute value of it should be 1. And also, I'm assuming this for N, so the absolute value of this should be by multiplicativity must be alpha, which is exactly okay. It's not exactly what I want to prove, it's only what I want to prove. Yeah, no, it's exactly what I Okay, we are not done. We are done under this assumption. So this is the easy part. So here as well, I'm not doing the full thing, but actually it's very easy. I didn't want this. I want to discuss. Well, time is gone. I want to discuss analytic geometry. This is just introduction. So I I didn't want this to be too lengthy. So I leave this to you as an exercise. Show that if n is a natural number, then the absolute value of n is bigger than 1. Or maybe a remark. The absolute value of n is always smaller or equal to n. I mean, we expect it to be n because we are used to it, but it must be smaller than n. Why? Triangle inequality. Doing n times. And of course, for non-Archimedean absolute values, it could be less than 1. So one can show that for Archimedean absolute values, it is always bigger than 1. So I leave this as an exercise. Actually, it is, if n is bigger than 1, so this is not a hard exercise, but again, it would be too lengthy for me to do it now, and I want to give you the idea. So, now, fix two guys, two integers, two natural numbers, and write n in m basis. Is this to go?
You're spinning with the camera now.
Okay. Okay. So what I'm writing now is n expressed in m basis, as we do usually with n being 10. So this means that I'm writing it like that. So this is some finite sum. Well, the index should go from 0 to some number r. AI's are always between 0 and n minus 1. And r should be then log n on base n, rounded up or down, rounded down. Having this, I can evaluate the absolute bound, the absolute value of n by means of the absolute value of m. So here is the triangle inequality and multiplicativity of the absolute value. And now I can evaluate AI. Well, I guess I'm using this, and I can evaluate AI by minus 1, by n minus 1. And m to the I, here I'm using this exercise. I can increase the power to r, and it goes up. Okay, so here I use in this. Now m is natural. No, this is the actual value of m. So m is less. I use this, and also I use this to increase the power without shrinking the value. Whatever. And okay, now I kill the dependence in on I, so I have. Oh, maybe. Sorry. I do keep this. Whatever I wrote was okay, but when I did write it this way, I didn't use that one, right? As you noticed on the left, I think. And so I'm not using this. I'm using that when I write like that. Okay. And sorry. And now let me replace R again by this, maybe slightly increased. So this again, this long line is an expression of the absolute value of n, or a bound on it by means of the absolute value of m. And actually this is what I care about, and this is just a noise. I want to kill this noise. In order to kill this noise, I will do this. I mean, this equation is correct for given n, for every n. Instead of n, I will take n to the k. So I will substitute here in this equation n to the k. So maybe I'll take it out right away. So I need to substitute here n to the k, but the k will go out. So let me please see if I can replace this by this. Actually, I could have written here 1 over k, right? I don't care that much. n minus 1 here, and here I have m slope and n times k. I choose to write it like that. And then I take the k root of this inequality and take a limit. All these get killed, and I'm getting. So as I promised, I kill this noise. And let me write it more symmetrically. Log without a basis on base E. I'm getting this. So I prove this inequality for every m and every n. And of course, it is correct also when I replace the roles of m and n. So actually, so it's equals, I don't know, some e to the alpha for some alpha. And so we get this. And this is exactly right. So the absolute value of a natural number up to a power is itself. And of course, because I can express every rational number. I mean, the absolute value of -1 is 1, check that. The absolute value of every rational I can express as a ratio of such things. My multiplicativity and the fact that raising to a power is a homomorphism, I'm getting that the absolute value of the real is standard absolute value up to power. Okay. just a remark. So, I didn't prove that every such thing is an actual absolute value. You should check. I mean, if alpha would be bigger than 1, this will not give you an absolute value. Convexity will fail. So, it's exactly those absolute values that appeared on the board earlier. Okay, so this theorem, again, explaining all the absolute values on Q, is called little Ostrowski theorem. And here is big Ostrowski. Now, Ostrowski go further and describes all Archimedean absolute values whatsoever. I mean, to be precise, whenever you have an Archimedean absolute value, I can first complete it, and then the description is nicer. So this is what we do. Complete Archimedean. Then either K is R, again up to power by some alpha less or equal 1. Okay, so I'll sketch a proof of that. I will not give full detailed proof. I can do it in the future if you ask me. But this, again, is not the subject of the course. I want to think that you've seen that here or there. I know that some of you did. Which is enough. So if the field is Archimedean, then this is very easy to check. It must be of zero characteristic. Just if it is not Archimedean, then it contains some prime field of order P, and you can't put an Archimedean absolute value on those. Check that. Okay. For example, it follows from the next slide, but it's much easier. Well, I guess just by axiom 2 of the axioms of absolute values, every okay, I mean, I'm leaving it to you to check this fully, and in any case, what we do get is that K contains Q, right? If it is characteristic 0, and since K is complete, and by little Ostrowski, the only possible absolute values are the ones we know, and the only Archimedean one is the real one. Then K contains a completion of Q with respect to whatever absolute value. Again, they give the same or similar metric structures. So K must contain R, and up to normalization, we may assume on R we get a standard absolute value. Now this is not entirely trivial. What I'm saying here is that my absolute value is known to be the standard absolute value to some power alpha, which is smaller than 1. I want to take now a power of alpha inverse and normalize it to be the standard absolute value on alpha. And we've seen before, at least I said, that it is easy to see that if you take a power of alpha smaller than 1 on an absolute value, you stay in absolute value. It is not true in general that if you take a power of alpha inverse, or alpha bigger than 1, say, then you stay in absolute value. But it is correct in that case, and this should be checked and be justified. Again, taking the power of alpha inverse here on the rings will take you to the standard ones, but it extends to a legitimate operation on K itself. Something to check. And okay, but assuming we've done this, I mean, there is no depth to it. It's just checking. We get that K is actually a real vector space, a standard real vector space, complete one, right? So it's a Banach space. Next thing I want to do is a complexification of it. So I want to add to make sure that K actually contains the complex numbers. And again, not entirely trivial thing to do is to see how to extend the absolute value to a complete absolute value on this one. So I'm taking the order 2 extension of K, and I want to say, I mean, it does follow from the fact that I stated. Maybe I should say this. Previously, I stated many facts. One of them was that I can extend absolute values over complete fields to larger fields, to algebraic extension. This fact is actually very easy over the non-Archimedean fields. And it follows from Ostrowski theorem for Archimedean fields. But this is the only case that I actually have to worry about. So here you really need to do something, to think a bit, but it's not very hard as well. And again, I don't want to get into it, I just want to give the idea. But once you've done that, we may assume with also loss of generality that K contains the complex number, the complex field. So K becomes actually a complex Banach space, and in fact it is multiplicative. So it's a Banach algebra. Okay, a Banach algebra. In which every element, or every non-zero element, is invertible. Now, the basic theory of Banach algebras, that I assume you know, tells that every operator in a Banach algebra, every element in a Banach algebra has a non-empty spectrum. And basically, by this, you prove, I mean, this is one of the basic results of Banach algebras, that K must be C. If every element is invertible, then it is just the field C. And the end of the stuff. So again, I think I gave a basic idea. It's not so hard to fill out the details here. If you wish, just ask, and I will do it maybe next time. Or for whoever wants to read about it but doesn't want me to lecture about it, I can give exact reference. Just ask me afterwards. For the parts that I did quote here but didn't fully prove. Just let me state the corollary, and then I will finish the first hour, the first lecture and the first chapter about absolute fields, and start to go to geometry. So just let me state the following corollary. So if K is a local field, this means that as a topological space, topology coming from the absolute value, K is locally compact. Not discrete. This definition of a local field. Then what? Maybe so in the Archimedean case, we have R. So if it is local field, it is easy to see that it must be complete. Okay, the local compactness gives completion, completeness. So in the Archimedean case, we must be real or complex. Now, what about non-Archimedean case? In characteristic 0, I must contain Q, and my absolute value must be one of those. So I'm assuming non-trivial, or I'm assuming non-discreteness. So, if I have a discrete absolute value on Q, I have a countable discrete subgroup which contradict double compactness, I guess. Okay, yes, I didn't choose my words carefully. So you can show that the absolute value on Q cannot be trivial, so it must be aperiodic, and so it means, since K, as I said, is complete, it must contain the periodic field for some P. So it must be a periodic Banach space. K. It's a vector space over the periodic which is complete, but it is local compact. So it must be finite dimensional. So K would be a finite extension. Of QP. Again, I'm not claiming to give you full details. I'm giving you ideas. This is just an introduction. And 3, well, what is left? Positive characteristics. So I mean, characteristic P. I surely contains FP, and all algebraic extensions of it are finite or countable, so I must contain some transcendental element, so I must contain T, and also the completion I must contain, so I must contain FPT. And again, by the same reasoning, I must be a finite extension of that. So maybe a finite extension of that is always FT for some finite field. Finite field. And this is an exhaustive list. So this is the most interesting fields. Of course, I guess these two are the most interesting, but those are interesting as well. Now, not the only interesting fields, as I tried to explain earlier. CP is very interesting as well, and you have others. So, after having T in the 8th law now, I will start doing analytic geometry of a field with absolute value.